Hi everyone, my name is Mila, and today I'll be doing a system design practice exercise. I'm doing this to help improve my skill sets, and I hope through that some of you learn something. But I stress, please double check anything you see in my videos. While I do have experience designing systems, there are people out there far better than I am, and I would rely on their knowledge rather than mine. With that said, let's jump right into it. Today, I'll be designing a chat service. I want to make sure that my chat service allows one-on-one communication, group chats, and ensures low latency. I want to support concurrent connections. I want to provide read receipts, typing status, and allow users to see the historical messages. I want to plan for over 5 million users with the option to scale as the volume increases. Whenever you have a service like chat, you typically provide that service across the world. And whenever you're providing service that's accessed from everybody on the planet, you want to have multiple data centers. And when you have multiple data centers, you want to route any connection that comes to your service to the most appropriate data centers. And the way we do that are through what are called load balancers. There are different types of load balancers, and there are different strategies when it comes to load balancing. Each one has its pros and cons, and that is a whole topic in itself, but I would encourage you to learn more about them. Because it's a global service, we will have not only global load balancers, but also we'll have regional load balancers. Some regions will have higher population density and more activity as opposed to other areas. When we hit our global load balancer, we will identify the region that is closest to the user and then pass that connection on to a regional load balancer. That regional load balancer will then use an algorithm to determine which server to send you to. Once again, there are many options: round robin, low latency, low load, each with its benefits and disadvantages. It's on you to determine what works best for your system and then adjust accordingly as your system matures. For our sake, we'll just simply use a simple round robin service. Once the server is determined, the connection is passed on to an API gateway. This gateway will help direct the request to the most appropriate service. In our case, what we want to do is have a persistent connection between the user and the service, especially when we want to have receive and typing status. So to do that, what we'll use is a WebSocket connection. Whenever you request a WebSocket connection, initially it starts with an HTTPS request that then is converted to a WebSocket connection. So, when the first connection comes in, we will pass that on to the WebSocket service, which will convert that connection to a WebSocket connection. But before we do that, we want to make sure that we authenticate the user prior to that. And to do that, we can use OAuth or JSON Web Tokens. If you're using a third-party application to verify the user, or if you're using your own data and login process, you'll use a web access token regardless. And we will use this to verify the user information. And once it's verified, we create the WebSocket connection. Once the WebSocket connection is established, the connection will now directly go to the WebSocket and no longer pass through the API gateway. To ensure that the connections are consistent, we want to configure our load balancers to have sticky sessions. What sticky sessions mean is that when a user reconnects, we will redirect it to the same server so that it can continue on with its session where it left off. WebSocket connections are stateful. That means they contain information about that state, and it's worth maintaining that connection when possible. Once that connection is established, we will then focus on processing the messages. But before we do that, let's make sure that we now save that session information to somewhere. And what we want to do when we create sessions is we want to store them so that they are easily accessible. The reason we store them is when the system needs to know how to communicate with a specific user, they will need to look up that user ID and find the WebSocket information so that they can direct that message back to them. Typically, this type of information is stored in a service like Redis. Redis is an in-memory storage service that allows you to store massive amounts of data with super fast access. So we will store all the user session information in the Redis service. All right. So now, if I want to know if I want to communicate with a user, I will simply look them up on the Redis server. I'll use their user ID to access their connection information and pass that information to that connection so that the client receives it. Now, let's take a look quickly at what a data might look like. We definitely will have a user table, and we will have a user ID as well as a username. We will have a user chat. Let me think about this for a second. We will have a user group, which will have a user ID and a group ID. So this will be for enabling group chat. So users can join a group and then they'll be able to communicate with more than one person at a time. We will also have user message, and we will have sender ID, receiver ID, and we can say that we can also do a receiver type ID. And the reason so the idea behind this is if it's a one-on-one conversation, the receiver ID will be a user ID and the receiver type ID will be a user. I can just simplify it like that. And if the user is sending it to a group, the receiver ID will be a group ID and the receiver type will be a group. Now you can split this up and simply have user message and then user group message. But this is just one other approach that we can take. Additionally, we want date stamp. We want read status. And looking at this, I think that covers most of what we want to do here. Okay. Over here, we might also want the user status ID, and we can use that to determine whether the user is online. And as I'm thinking this through as I'm trying to figure it out. And we can also have last online date stamp. That will allow us to know when the user was online last. Let me just create some consistency here. All right. So that's what our data will look like. And we definitely want to take this into account as we're designing our system. All right, so now let's go on to capturing a message and then delivering it. So as messages are coming in, what we want to do is make sure that they are not lost, because we don't know what that pipeline looks like and how long that process might take and what can potentially happen there. So what we do is that as soon as a message is sent to the server, it is stored in a message broker like Kafka. Kafka, think of it as a database. It just stores data that is accessible through subscribing to the different topics that Kafka has been configured to provide. So the messages go immediately into Kafka, and Kafka is highly reliable and persistent, meaning that if your server should restart, the messages will not get lost. At the other end of it, we will have a message service. The message servers will read from the the Kafka topic and then determine what to do. It will determine whether this is a group message or if it's an individual message. If it is an individual message, it will look up the information, look up the user ID in the connection pool, and then based on the information, send a message to the correct WebSocket connection and read and send it to the client so that they can receive the message. Additionally, what we also want to do is save the data so that it just thinking about this a little bit more, it might be necessary to instead of writing, we'll call this new message Kafka. So this is where all the new messages come in from. And then what I want to do is make sure that I don't overload the message service that reads it. This will be send message Kafka. All the messages in here will be for users who are waiting, who need to be sent a message. So I'll get rid of this. I will have the message service store that information into let's see, I'm thinking this through, guys. I'm sorry, I'm trying to think this through. I will have it determine what you... Jeez. Okay, there are multiple ways of doing this here. Okay. So what I need... Okay, I know what's missing here. There is a group service here. And basically what happens is when the user, when the message service receives a new message that needs to be sent to a group, it passes that information to the group service. Otherwise, it will write directly into the send message Kafka service because it knows exactly what user it should go to based on the sender ID that we have over here. I mean the receiver ID and the receiver type. Otherwise, if the receiver ID is a group ID, we'll send it to the group service. The group service will then, we can have a separate Redis service here. We'll call this a Redis server. This should. Now the reason I'm separating these two is because they serve different purposes, and by having multiple different servers, you can increase the complexity, but if one system should fail, the other will be still operational. So the group service will grab all the users who belong to that specific group, and then write messages to send message Kafka's topic. Now, to make sure that we have, let's continue this. So we get a new message. We determine it's directly to a user, so we write to send message Kafka topic. If we determine it's a group message, we get the users that belong to that group, and then we write that to the send message Kafka topic. And then over here we have a send service. And the send service will subscribe to the send message Kafka topic. When it gets a user ID, it'll look up the connection information and then send that to the appropriate WebSocket service, and which will send that information to the client. Now, that takes care of us enabling one-on-one and group chats. And it also ensures low latency because we're utilizing Redis, and we're using a micro-architecture approach so that each process is responsible for only one thing. The next thing we need to do is store historical data. So we will have a DB here, and for something like this, where we're simply want to store messages and there's really not that the relation, the structure of the data is pretty simple and flat, and there are no complex relationships. So we can go for a NoSQL database like MongoDB. That will allow us to save the messages, and in the future, if we decide that we want additional information and additional data points, we can save that additional data without impacting previous rows, previous documents that have been inserted into the DB. So this will hold chat activity. Now, what we also want to do is have another database that holds the user information. And for that, we use a SQL database. And NewSQL is the newest technology when it comes to SQL DB. It's got the benefits of NoSQL, like MongoDB, which is designed for the cloud to be scalable horizontally, while traditional SQL DBs were designed to be vertically scalable. NewSQL allows all those benefits we've seen with NoSQL database integrated into this new system. Now, whenever you come here and you don't find that data in the cache, you simply get that information from the SQL DB. Now over here, what we'll do is we'll have a chat activity service that will read from all the new messages that are going out and write them to the DB in predetermined batches. Rather than doing one insert at a time, we'll do batch inserts, reducing the overall load on the system. Okay, so now what we want to do is, so now we've taken care of the historical chat sequence as well. So now what happens is when a user connects to the service, we will have another Redis server. This one would be history, chat history. Oops. So when a user connects for the first time, we will connect to the history service. The history service will look up the conversation that the user is in and determine whether there is a history behind that, and get that history from the DB. Okay, so I just realized that we could actually simplify this and reduce this to simply group ID. The only difference between one-on-one and group chat is the number of users that are in a group. So one-on-one is simply a group that only consists of 2 people, and for more people, you simply add additional people to that group, and you can always add more people as you want. All right, so that takes care of that. Okay, now what we also want to do is now take care of the red status. So when a user comes in, we want to make sure that we capture the event that the user has read the message. And just like we'll have a topic, we'll have a Kafka topic that's simply for read status, and then we'll have a read service that subscribes. The event will be sent to the service that says this message has been read. It'll give the message ID. The user, the read service will subscribe to this topic. It will then write to this sent message service. And remember, you can have different messages here. All sorts of messages can be sent in the sent message Kafka topic. You would just have different codes for them so that the client knows how to interpret them. And then what we also want to do is and by writing to this, it will read that information, send it to whoever needs to know whether that message has been read, and then the chat activity service will also know how to interpret that and update the specific data for that specific message, and then send that to the user. Now, the last thing we need is a typing status. And for this one, I'm trying to think here, is we need this to be pretty quick. So as soon as the event comes, we will have a we will have a typing Kafka topic that the typing status pays attention to. And then writes to a topic that is for typing. So the message that we send to the client will be simply, hey, somebody is typing. Now, when we think about scalability and supporting over 5 million users, it's about redundancy, it's about auto scaling, and what the infrastructure is built on top of. Some of the things we will definitely be doing is, for our DBs, they will be databases as a service, and they will be managed, scaled horizontally as necessary, partitioned. Well, for databases, the term is sharded, so that the load is distributed to different servers. We will have multiple Redis clusters, and that allows us to sync the data across the globe, as well as ensure redundancy. We will have our services that process and act on these messages built on top of a K8 infrastructure, and we can have those horizontally scaled based on configuration. We'll also have cluster scalers that will look at each individual K8 node, determine if it's hitting its peak performance, and if so, create additional instances. And then also we want to make sure that we have multiple data centers across the world, and ensure that our load balancing algorithms are optimized for what we're using. If we find that this architecture needs additional optimization, we might even consider edge computing for locations or regions where the population is really high, and have data centers local to those specific regions. This was my attempt at designing a chat service. Once again, guys, I was doing this on the fly. Double check anything I say. I hope you learned something. I'll review this video myself and see where I can make improvements. Thank you so much. Have a wonderful day.